In this video, we're going to be looking at some of the standard manipulator types. In previous videos, we've learned that 3 degrees of freedom are desirable in a manipulator because 3 degrees of freedom is the minimum number required to allow the end effector to reach a 3-dimensional space. In other words, to allow the manipulator to have a 3-dimensional workspace. We've also learned that there are 2 different kinds of robot joints: prismatic joints, which allow linear motion, and revolute joints, which allow rotational motion. As a result, there's a limited number of different kinds of arrangements that you can have of 3 joints where each one is either a prismatic or revolute joint. That gives us a limited number of standard manipulator types. In this video, we're going to look at each of these different types, and we're going to draw a kinematic diagram for each one of them. I've written here the 5 types of standard manipulators. The Cartesian manipulator, which consists of 3 prismatic joints in series. Cylindrical, which is 1 revolute joint followed by 2 prismatic. The spherical manipulator, which is 2 revolute joints followed by a prismatic. The Scara manipulator, which is also 2 revolute joints followed by a prismatic, just in a different arrangement compared to the spherical manipulator. And the articulated manipulator, which consists of 3 revolute joints in series. We'll look at each of these manipulator types in action, and I'll show you how to draw the kinematic diagram for each one. I'm showing here a video of a gantry robot. A gantry robot is the same thing as a Cartesian manipulator. It consists of 3 prismatic joints, one which allows linear motion in this direction, another which allows linear motion in the perpendicular direction, and a third joint allowing linear motion in the vertical direction, mutually perpendicular to the other 2. Let's take a look now at how we would draw a kinematic diagram for this robot. If you remember from earlier videos, a prismatic joint looks like a box or a cube with a square next to it indicating the direction that motion is occurring. So this box that I've drawn represents the Cartesian manipulator x-axis motion. Next, I need to draw a second joint that will provide me with y-axis motion. The second joint is connected in series with the first joint, so I'll attach the second cube to the end of the stick here that's attached to the square of the first joint. In this case, the motion for this axis will be into and out of the page. So I'll draw this square in a direction that is perpendicular to the first square. And I'll add a stick coming out of the page indicating the direction of motion. The last piece that I need for this kinematic drawing is an axis that goes in the vertical direction. And once again, this axis is connected to the motion of the second axis. So I'll draw it connected to the stick. For this axis, the motion is in the vertical direction, so I have to draw the square coming out of the bottom. And I'll show the stick showing the direction of motion going down. And this is my drawing of a 3 degree of freedom Cartesian manipulator. I'll show you a professional drawing of one now in a moment. Here's a professional drawing of the kinematic diagram for a Cartesian manipulator, along with a picture of the robot that this drawing is supposed to represent. You'll notice that in this drawing they have labeled 3 variables, D1, D2, and D3, representing the displacement of each of these variables, or each of these joints. They've also labeled Z0, Z1, and Z2 as the lengths of each of these links. Next, let's take a look at the cylindrical manipulator. I'm showing you a video here of a cylindrical manipulator. I want you to notice that it has a prismatic joint in the vertical direction. It also has a rotary joint at its base. And lastly, it has another prismatic joint that allows it to have a radial extension. This makes it an RPP manipulator, revolute prismatic prismatic. Let's try to draw a kinematic diagram for this kind of manipulator. The first joint is a revolute joint at the base, so I'll start by drawing a cylinder. The next joint is a prismatic joint that has vertical motion. So the next thing I'll do is draw a box attached to this stick coming out of the top of the revolute joint at the bottom. This prismatic joint allows motion in the vertical direction. So I'll draw my square showing the direction of motion at the top of the box. And I'll show the stick coming out of the top of this, joint, showing the direction of motion. The last joint is another prismatic joint that allows linear motion in the radial direction. In order to achieve that, I will draw another box attached to the second joint. And this time the direction of motion is horizontal, and so I'll draw this square over here. And I'll draw the stick once again coming out, showing the end effector, which is located over here. This is my drawing of a cylindrical manipulator. Let's take a look at the professional drawing now also. Here's the professional drawing of the cylindrical manipulator, along with a picture of the robot that the drawing is supposed to represent. You'll see that we have a revolute joint at the base with an angle of θ1. That's the variable that represents the rotation of a revolute joint. Attached to the top of this is the prismatic joint with the variable d2, showing that this joint allows linear motion in the vertical direction. And finally, we have a third prismatic joint with the variable d3, showing a linear motion allowable in the radial direction. Next, we'll take a look at the spherical and Scara manipulators, both of which are RRP manipulators, 2 revolute joints and 1 prismatic, just in a different arrangement. I don't have a video of the cylindrical manipulator, but I'll show you a video of a Scara robot, and then I'll show you how the 2 kinematic diagrams are different between the Scara and the spherical. Here's a video showing a Scara robot in operation. Notice that it has 1 revolute joint at its base, followed by a second revolute joint, and the last joint is a vertical linear prismatic joint. This type of a robot manipulator is very good for pick and place operations, as you're seeing it perform here. It's good at pick and place because the robot is very stiff in the vertical direction, and so it can carry a fairly high payload to pick up and place. Let's go ahead and draw the kinematic diagram for a Scara manipulator. It starts out with a revolute joint at its base, followed by a second revolute joint. The second revolute joint might be offset from the first one, but its axis of rotation is in the same direction. It's parallel to the axis of rotation of the first joint. Finally, we have a prismatic joint. And this prismatic joint has a direction of motion that is vertical. So this is my drawing of a Scara manipulator. Let's take a look at the professional drawing for this type of manipulator. Here's the professional drawing for a Scara manipulator. It looks similar to mine, just a lot nicer, and it shows the theta 1 of the base joint rotation, the theta 2 of the second joint, whose axis of rotation is parallel to the first joint's axis of rotation, and finally a prismatic joint allowing vertical linear motion. Here's a drawing of the spherical manipulator, which is similar to Scara in that it's an RRP manipulator. The difference between a Scara and a spherical manipulator is that in the spherical manipulator, the second revolute joint has an axis of rotation that is perpendicular to the axis of rotation of the first joint. And its prismatic joint also is not a vertical prismatic joint, but it's a prismatic joint that allows radial motion. As a result, the spherical manipulator is not as good for pick and place operations as the Scara manipulator. Finally, the last type of manipulator we'll look at is the articulated manipulator. A manipulator that consists of 3 revolute joints in series. We've seen the articulated robot before in this video of this robot ride. The articulated manipulator is perhaps the most dexterous of the different types. However, it's also the most mathematically complex to do the kinds of calculations that need to be done. So this type of manipulator is frequently used for things like robotic painting, robotic welding, all kinds of things that require very precise and complex motions of the end effector. Let's take a look at its drawing. The articulated manipulator starts with a vertical revolute joint, followed by a second revolute joint that has an axis of rotation perpendicular to the first joint. The last joint is also a horizontal revolute joint, so that the third joint's axis of rotation is parallel to the second joint, but perpendicular to the first joint. And that's my drawing of an articulated manipulator. Let's take a look at the professional drawing. Here's a drawing of the kinematic diagram for an articulated manipulator, along with a picture of the robot that it's supposed to represent. You'll notice that in this picture, the different parts of the articulated manipulator are labeled, starting with the body, followed by the shoulder joint, and finally the elbow joint. These labels are used because the articulated manipulator is similar to the structure of the human arm. Throughout the first part of this class, we'll be using these 5 standard manipulator types to learn about robot kinematics. Because these types are standard, if we learn the concepts for these 5 types, we will be able to apply the concepts we learn to virtually any type of robot that you would encounter in industry